Hello. Today we continue the introduction to the finals of Flemish Mathematical Olympiad this year. The VWO stands for the Flemish Mathematical Olympiad, and this competition is designed to the students in the year 5 and year 6, so year 5 and year 6 in the high schools of Flemish region. The final competition consists of 4 problems as well, and the competition time are also 3 hours. This year, there are 4 problems, and 2 out of 4 are apparently algebraic algebra problems. One from geometry, and another comes from combinatorics. Let's start first. Let's start with the first question. Yeah, the problem states a point P lies outside of a circle. There's a circle C in the figure, and through P there is a straight line M, which intersects at the circle C at point A and B. And the circle C1 passes the point A and is tangent to circle C as well. So C is the tangent point. And another circle, circle C2, passes P and B, and C2 is also tangent to the circle C. And we are required to prove that the different radius between C1 and C2 does not depend on the location of P or the choice of M. So meaning that P is a dynamic point, M is a dynamic segment or dynamic straight line, but the difference between the C1 and C2 is a constant. It's constant towards the position of P or direction of M. So this question, so we know that for the tangent point A, if we draw a tangent line through A, so this line passes the center of C. So let's say it's O is the center of C, and the center of, for example, the center of the C1. So let's say it's O1. O1 is center of C1, and O is center of circle C. And we draw again a tangent line through B. So where it passes over O and B, and also the center of C2. So we say it's O2 is the center of C2. Okay. So we just connect the PO2 and PO1. So we just connect these 2 points. Okay. And it's clear that the AO is, let's say, the radius of the circle C, let's say is R, and BO is also R. So the triangle ABO is isosceles triangle. So the two angles are equal, right? And same for the triangle AO1 and P. So AO1 and P. So in this triangle, the AO1 equals to the PO1, whereas the radius of the circle C1, so let's say it's R1. So that means the angle, this angle, equal to this angle as well. So then we have the angle, a mark angle with another color. Okay, it's blue. The blue angle equals to the blue angle because they are all equal to the angle O1, A, and P. So they're all equal to this angle. So from here, we can conclude that the two lines or the two segments, BO is parallel to PO1. Yeah. Okay, so we do the same. If we do the same, we can find that this angle equal to this angle because the O2PB in the triangle O2PB, they are the two radius. So it's the R2, and this one is also R2. So the triangle O2PB is also isosceles triangles, right? And we know that we can also mark in blue this angle equals to this angle and equals to the OAB as well. So here we can say the OAB equal to the angle O2PB, right? O2PB. And from here, we can also show that the O2P is parallel to AO or the AO1. So from here, 1, 2, from the two pairs of parallel lines, we show that O2 PO1 O is a parallelogram, right? So this is a parallelogram. And from here, we know O1 O equals to PO2, which is the radius of the second circle. And AO1, the O1A or the O1A is the radius of circle 1. And AO is the radius of the circle C. So from here, we know that R equals to R1 minus R2, which is independent on the location of P or the direction of M. So that is the proof. That is proof. Okay, we go to the second question. The second question is algebra, something about algebra. There we have a function equations. Fk plus 2 times f1 minus k equals to k squared. And this function equation is satisfied for every integer k. The first question is asked to determine f3, and second question is asking to prove that fk is no integer. Okay, so let's replace k with n. Okay, then we have fn plus 2 times f1 minus n equal to n squared. Yeah, and then the sixth step, we replace k with 1 minus n. It's 1 minus n. So here we have f1 minus n plus 2 times of fn equals to 1 minus n squared. So here we have a system equations. So we have two variables, two equations. Two variables are fn and f1 minus n. We have two equations. So it's very easy to find the solution. Fn equals to n squared minus 4n plus 2 over 3. So the first question is very easy. So F3 is actually, we put 3 in, and we have minus 1 over 3. Yeah, just replace n with 3. Second question, we have to prove that Fn or Fk is never be a integer. So here we can just rearrange a little bit. Fn equals to 3n squared minus n minus 1, and then minus 3n plus 3, right? And where we have n squared minus n divided by 3 minus 1, no, minus n and plus 1. Okay, so this is an integer. In the first part, we have to prove that the first part won't be an integer in any case. So we just consider the divisibility of n by 3, or the n modulo 3. So there are 3 subcases. First one, when n is congruent to 0 modulus 3, and in this case, the n squared minus n minus 1 is congruent to minus 1 modulus 3. So, which is not divisible by 3. So Fn is no integer. It's a no integer. Right? Set case is that when n is congruent to 1 modulus 3, so that's very similar. So n squared minus n minus 1 is congruent to minus 1 again, modulus 3. And of course, in this case, Fn is not an integer. The last case, when n is congruent to 2 modulus 3, and then the n squared minus n minus 1 is congruent to 4 minus 2 minus 1, which is 1 modulus 3. So in this case, Fn is again no integer. So as concluded, in all the 3 cases, the Fn is a fraction. It won't be an integer. So that is the end of this proof. Question number 3. And this is something about polynomial, right? The px is a polynomial equal to 1 plus x plus square x plus cube x until the 2024th power of x. We have to find the remainder polynomial when p, the x to the 2025th power, is divided by px. Okay, so we can just write, okay, the p x to the 2025th power equals to a qx, example, is quotient polynomial, times px plus rx. So rx is actually the rest, rx is the rest polynomial, right? So we know that the degree of px, or the highest power of px, is 2024, right? So from the definition, we know that this is the highest power of x in px. The degree of px will be 2024. So from here, we know the Rx, because Rx is the rest polynomial. So the degree of Rx will be no more than 2023. Yeah, it must be smaller than the degree of Px itself. Okay, so that's the first thing we know from here. Now consider the roots of Px equal to 0. So think about this. Think about these equations. And it's apparently, when Px is 0, so it's apparently x equals to 1 is no solution. It's no root. Yeah, it's no root. Or we can say x cannot be 1. Cannot be 1, right? Because if we put 1 in, so you have a 1 plus 1 plus 1. So that won't be 0. Okay, so then we can just reform this equation. So 1 plus x plus x squared plus dot 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 plus x to the 2024th power, whereas actually it's 1 minus x 2025th power divided by 1 minus x. So that is easier because that's the sum of a quadratic sequence, right? With a common ratio of x. So we get px equals this. So if we set to 0, we know that x cannot be 1. So it's very easy to find 2024 roots of these equations where the xk equals to ei. So that is the unit circle, yeah, divided by, so the 2 pi is divided by 2024. And for each angle, you get n roots. So that's ei 2 pi divided by 2024 times k. But where k cannot be 0, because if k is 0, x will be 1, right? So k starts from 1 to dot 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 till 2023. 2024. Yeah. Yeah. Sorry. Here we have a arrow, a mistake made. It's not 2024 because it's 2025. Why? Because here we have x to the power of 2025. So the unit solution in the unit circle is xk equals to ei 2 pi divided by 2025 times k. So here we have k equals to 1 to till 2024. So in total, there are 2024 roots. And we know that for each k, or for each xk, we know that xk is ei 2 pi divided by 2025 times k. So that is the units, the roots. So from here we have xk to the 2025 power equals to ei 2 pi times k. So here is always a multiple of 2 pi. So we know that it will be always 1. So for each k, xk to the 2025th power is 1, right? So now we have a p x k 2025 power because it's equals to p1, yeah? Because this one is always 1. And p1, what is p1? p1 is 1 plus 1 plus 1 plus dot 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 plus 1. And how many ones we have? 2025s. So we have 25 ones. So we'll give you 2025. Yeah. And in another words, by the definition, so still remember the definition? So in this definition, we put the pxk to the 2025th power in, and we know that qx, here we have also qxk times pxk and plus rxk. Yeah. because for each xk, the pxk is 0. Yeah, because xk is one root of px equal to 0. So the first term is 0. So we get is rxk. And it is 2025. Yeah, from here, yeah, 2025. So we have these equations. And how many xk are? So we have 2024 different xk's which meet this equation. And in the other end, we know the degree of Rx is no larger than 2023. So that means the Rx is equals to 2025. So Rx itself is a constant polynomial. Otherwise, we won't have 2024 roots for this equation. So that's why we got the remainder polynomial Rx is 2025. So 2025 is the answer to this question. The last problem is combinatorics. I think that's interesting. It stated that in one of the class, so class 5, there are 26 students. And everyone has a fixed place in the classroom. Adam is the first one who enters the classroom, but for him, it's a little bit confused on that day. So normally, he should choose his own place. But on that day, he chooses randomly a seat. Yeah, it can be his own seat or a seat of others. And the other students entered one by one, and they are not confused. But if the C, its own seat is still free, and they will select his own or their own. If not, meaning that if their own seat is occupied already by somebody else, and they will sit also a seat at the random occupied chair. So they select randomly an occupied chair, just like Adam. And it's asking Zhu is the last one. So Zhu enters the last. What is the probability that she can sit at her own seat? Yeah. So remember, it's 26 students. So A, B, C, till Z. Okay. So for this question, we first claim our answer. So we claim for any n no less than 2, meaning that for students, if we have n students, no matter 25 or 26 or 27, if we have n students, which is bigger than 2, no smaller than 2, the chance of the last student can be Z, can be others. And the last student is able to sit on his own seat. The probability is always half. It's always half. So that's our claim. Well, the answer is actually for 26 students. The probability is also half. So we prove our claim using mathematical induction. And in this case, we use the complete mathematical induction. Okay. So first of all, we just try if n is 2. So the base case when n is 2. So we have A, Adam, and B. Yeah, we have 2 students, and there are 2 seats, A and B. So we have students, A and B. We have seats, which is also A and B. Yeah. So in this case, it's very easy. When A when A is selecting his own seat A. So in this case, we have a half probability. For A is choosing A, and of course now B is able to choose his own seat B. So then the second step is 100%. So actually we have 1/2. Yeah. The second case, so that is the first case. The second case is that if A choose B seat, so B choose the seat of B, and in this case, of course, B has no chance to set his own place, so B will choose A. So in this case, A choose B is half probability, but at the end, B choose B is 0. So it's no no probability or no chance that B selects its own. So that will be 0. So in total, the P equals to half plus 0, which is half. Yeah. So the statement or our claim stands for n equal to 2. Now think about n equal to 3. Okay, we do it a little bit more to show our strategy. So now for the students, we have 3 students, A, B, C, okay? And for the seats, we have also 3 seats, A, B, C, okay? So the first case is again, A, select his own seat. So Adam selects his own seat, and according to the rules, B will select also his own, and C will select also his own. So in this case, A selects A, so here we have 1/3 probability that A selects A, and for the rest, we have 100. Yeah, because according to the rules, everybody will select his own. And for the last student, it's also possible that he or she select his own. So then we have 1/3. Yeah, then we have 1/3. In the second case, if A selects C instead, directly select C. And in this case, there's also 1/3 probability. And now for the rest, we still have a B and C to select. And then what is seat here? The seat is A and B. So no matter how B and C select, the seat C has been already occupied by A. So that is 0 probability that C can still sit her own seat. So that's why we get 0 in this case. But still, we have the third case. The third case is that A select the seat B instead. Okay, in this case, then we have still B and C, 2 students, and the seats we have A and C. So we have seat A and C. In this case, we still say, okay, if A selects B, so that is probably 1/3. And for this case, BC, so if B selects C, there's no chance. If B selects A, and there's 100% chance, so actually there's half of the chance. That is half of the probability that C is still able to sit as her own seat. So it's 1/3 times 1/2. So here we have 1/6. So the whole probability is 1/3 plus 0 plus 1/6, which is also 1/2. So our statement is also correct for n equal to 3. Now, we assume our claim or our statement is true for n equals k. Okay, so for n equals k, the p is also half. So that is the assumption step. Now we have to prove that for n equal to k plus 1, the p is also half. We have to show it stands also for this case. So for n equal to k plus 1, we have students that says A and S1, S2, dot, 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 SK minus 1, and SK. Okay, so in total, we have K plus 1 students. Yeah, the seat is also like this. So A, S1, S2, dot, 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 SK minus 1, and SK, where SK is the last student enters classroom, and A is the first one who enters classroom. Okay, so we divide this process into three different cases. Case one, when A selected his own seat, and we know that there's no other possibility, because then the B will select B as well, or not B, sorry, as S1 in this case, not B, no B anymore. So S1 will also select S1, and S2 will also select S2. So till the end, SK will select SK. So A selects A, the chance is 1 over K plus 1. Yeah, because in total there are K plus 1 seats. So the chance is 1 over K plus 1. And for the rest is 1, 100% sure SK will select his own seat. So in this case, the chance is 1 over K plus 1. Okay. Second case, when A directly select SK. Yeah. And no matter how the rest story goes, the SK, the seat SK, has been already occupied by A. So there's no chance for SK to select her own seat, right? So the probability will be 0. So the probability that A selects SK is again 1 over K plus 1. Yeah. And the rest is 0. The rest is 0. So in total, there's 0 that SK can sit on her own seats. Okay? The third case is something in the middle. So if A is selecting an SI seat, so where I, so we defined I is bigger than 1, but smaller than, no bigger than K minus 1. So because when I is K, we already discussed in the case 2. Yeah, in the discussion of SK, K is the last one, right? So now we discussed I is no smaller than 1, but no bigger than K minus 1. Yeah. So in this case, SI. So we have actually SIs here. We just list SIs here. And for the S1, in this case, S1 will again select S1 because S1 seat is unoccupied. So S1 will select anyway S1 seats as we defined in the question. If their own seat is still free, they sit there, right? So S2 will select S2. There's no other possibilities until here, Si minus 1 will again select Si, will select Si minus 1. Okay, and for the rest here, so Si plus 1 till Sk. In this case here, we just say that seat A is still free. So we say A is I plus 1 dot 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 till Sk. So in this case, we have to calculate how much the probability is that SK is able to sit on her own seat. If we assume, we just assume, or if we regard the plate or the seat A as a seat SI, because here the SI is free, because his own seat is already occupied by Adam, by the first player. So SI now, it becomes a new Adam. Yeah, he is able to select A or the other seats from the other students. So SI is now the first student in the classroom. If we think about the question becomes not K plus one student, but K minus I plus one students. For the rest students, there are all still some student here, and SI is a new Adam. Yeah, he can select Adam seats. He can select also other seats. So now we can use the assumption in the mathematical induction. So for any n equals to k, or it should be equal or smaller than k, because it's complete mathematical introduction, right? The p is always half. So we know in this case, the rest part we have half. The rest part, the p, the probability is half. And what about the first part? The first part, A is selecting SI. So that's the same as 1 over K plus 1. Yeah. So that's his only possibility of 1 over plus 1. And for the intermediate steps, S1 till Si minus 1, that's all confirmed. It's all the same as 1 because there's no other possibilities, right? And for the rest part on the right, from Si to Sk, the probability is half, as we assume in the assumptions, right? So in total, we just the map is just like 2 times k plus 1, 1. Yeah. Now let's add them up. The case 1, so the whole p is case 1 is 1 over k plus 1. So that is case 1 from here. Case 2 is 0. Case 2 is 0. Case 3 is 1 over 2 k plus 1. But how many case 3 are here? I, how many i's are possibility? So how many i's are possible here? So I is starting from 1 to k minus 1. So in total, we have k minus 1 such cases. So we have to times k minus 1, meaning that I can be 1, 2, 3 till k minus 1. So there are k minus 1 cases like case 3. Yeah, so we have to multiply k minus 1. So here we have k plus 1, 1, that's the first case, second case 0, and 2 times k plus 1, k minus 1. And that is 2k plus 1 and 2 plus k minus 1, which is half, which is also half. So that means for n equals to k plus 1, the probability is still half. So per the mathematical induction, for all the n bigger than 2 or no smaller than 2, the probability is half. But for this case, specifically, we have 26 students. Of course, the chance or the probability that the last student is able to sit on her own seat is half. Okay, so that is the end of the introduction to the final problems in the VWO this year. I think the difficulties of the 4 problems are suitable for the JWO they are a little bit too easy. But for the VWO, is suitable, a little bit easier probably, but is suitable for the levels of the Flemish students in high school. Okay, see you next time.